let's talk about orthonormality and integration in spherical polar coordinates. If we take a look at the postulates of quantum mechanics, right, we know that every physical system is described by a wave function. That this wave function, its absolute square, that describes the probability distribution for that system. These wave functions, they need to be orthogonal. They also satisfy an eigenvalue equation. An operator operating on the wave function of the system equals a constant times the wave function. These wave functions, also sometimes called the eigenfunctions of the system, right? They form a complete set of orthogonal normalizable functions. Why is that important? What does it mean? Well, there are an infinite number of functions that satisfy the Schrödinger equation, but only one makes physical sense. How are we going to figure out which one that is? Well, let's remember that the probability of finding a particle in a certain region of space between the coordinates tau1 and tau2, that's given to us by this integral over the absolute square of the wave function. So we need to integrate the absolute square from tau1 to tau2, and that will give us the probability of finding the particle in that region of space. Now, a good wave function is normalized to 1. That means if we integrate over all space, this integral must be equal to 1. Why is that important? Because if a particle exists, then the probability of finding it in the state that it occupies must be unity, must be equal to 1. And that allows us, by setting this value of the constant out here, that allows us to choose the right wave function that solves the Schrödinger equation and also makes physical sense. So, what does the normalization integral look like? And it actually depends on the coordinates of the system. If we had a 1D system, it only depended on x, then we'd take the complex conjugate of the wave function multiplied by the wave function and integrate over all values of x. That should be equal to 1 for a normalized wave function. If we had 3D, right, x, y, and z, still a linear system of x, y, and z, but then we need a triple integral over dx, dy, dz. This entity here, this triple product, that's called the Jacobian, the volume element of the system. Now, we don't always use linear coordinates, and in particular for central field problems such as atoms, spherical polar coordinates are much more appropriate and make it much easier to calculate the values that we need, the energies of the system, for instance. And for that, we need a different Jacobian, r squared sine theta dr d theta d phi. R is the radial coordinate, theta is the polar angle, and phi is the azimuthal angle. And we have to integrate over the appropriate limits, 0 to 2 pi for phi, 0 to pi for theta, and 0 to infinity for r. Don't forget to multiply by this Jacobian to get the right value of the probability over this region of space. And if we integrate over all space, again, a normalized wave function will give us a value of 1. So let's do one of these triple integrals, right? If we have a wave function, like we're often going to see, our wave function is a function that can be factored into a function of the radial coordinate, a function of the polar angle, and a function of the azimuthal angle, multiplied by some normalization constant. Well, if we can factor the wave function into 3 terms like that, we'll see that we can also factor this triple integral into a product of 3 integrals. And those integrals, we only integrate one variable at a time, right? Phi, theta, or r. Now let's actually calculate one of these for the hydrogen atom, right? Here are 2 normalized wave functions that describe excited states of the hydrogen atom. All right, psi1 and psi2. And what we want to do is we want to use the normalization condition to find this normalization constant for the first wave function there, psi1. All right, so we're going to integrate over spherical polar coordinates in 3 dimensions, right, to find out what the value of the normalization constant is for psi1. All right, our wave function down here is a real function. If it's a real function, then the complex conjugate is the same as the wave function. So finding the absolute square, we just have to square the wave function altogether. And now we're going to substitute that into here, obtain our triple integral by multiplying by the appropriate Jacobian, which allows us to factor this into a product of 3 integrals. We need to evaluate this product of 3 integrals. We can do that, for instance, in Mathematica. And we find the value of the integral over phi, that's pi. And then if we integrate from 0 to pi for the integral over theta, we'll find 4/3 is the value. And finally, the radial part, if we integrate 0 to infinity over the radial part of the wave function, we get 24a0 raised to the 5th power. Now we need to multiply all 3 of those terms together, right? To get the final answer, let's divide through by n squared, and then finally solve for n1. The normalization constant of wave function psi1 is the square root of 1 over 32 pi times a0, the Bohr radius, raised to the 5th power. What about orthogonality? Orthogonality, right? If 2 wave functions are orthogonal, they have no net overlap. The orthogonality condition, right, is then also defined by an integral. This time it's an integral of 2 different wave functions. A wave function times a different wave function's complex conjugate, and we integrate over all space. So let's confirm that these 2 wave functions that describe the hydrogen atom, that they describe 2 different states of the hydrogen atom, therefore they're eigenstates of the hydrogen atom and must be orthogonal. In this case, we're going to have to integrate again over spherical polar coordinates in 3 dimensions. We actually don't have to worry about the normalization constants. They're never equal to 0, so they're not going to, for this problem here, they're not going to make this equal to 0. So let's just concentrate on the terms involving r, theta, and phi. Here we have our 2 wave functions. Again, they're both real functions, so the complex conjugate is the same as the wave function itself. And then we're going to substitute in for psi1 and psi2 here and form our triple product, 3 integrals, 1 over phi, 1 over theta, and 1 over r. Now, if you have a triple integral, and you're trying to see if it goes to 0, and it is the product of 3 functions, if any one of those terms goes to 0, then the entire product goes to 0. So once you've found a term that goes to 0, you can stop. And if we look out here, we have an integral over symmetrical limits, right, all the way around 2 pi, from 0 to 2 pi, of an odd function, and that is going to go to exactly 0. Therefore, the product goes to 0, and we've shown what we wanted to show. The 2 wave functions that we've chosen of the hydrogen atom are indeed orthogonal.